Hi everyone, welcome to our latest episode of Going Native, and special shout out to Downtown Dave and Mematrasoft C++ Jedi for correctly identifying this month's episode. So Steve, we're going to be talking about await. Take us away.
Yeah, so last month we did our Linexa report about the things that had happened at the C++ meeting in Linexa, Kansas, and all the things that had done that. We forward refed to this episode where we're going to dive in a little bit deeper on await and coroutines. And so today we'll be interviewing Gor Nishanov, who is a member of our team who has been working with the committee to get that through. Welcome to yet another episode of Going Native. I'm here today with Gor Nishanov from the Visual C++ team. Gor, you've done one of these before, but it was a while ago. Can you reintroduce yourself for our audience?
Sure. I'm Gor Nishanov. I'm a developer with Visual C++ team, and I work on design, standardization, and implementation of coroutines for C++ 17, hopefully.
Why do you say hopefully?
Well, hopefully is that it got accepted by the evolution group and sent to the core language, but the shipping vehicle has not yet been agreed upon.
I see.
So it can either go directly to C++ 17, or maybe it will be a technical specification first to try it out before it is adopted. And
got it. So we keep saying await and coroutines. Let's tell folks what that is. What is a coroutine?
Well, coroutine is something very, very, very old. It was introduced in 1958, which is 57 years ago. And back then, actually, it was quite possible because it was an extended control flow where you can jump out of the function and then jump back in to continue where you left off.
So there's definitely a relationship to like the asynchronous programming of today. Is that the right way to think about it?
Sure, and actually probably the asynchronous programming is one of the motivations why coroutines are being reintroduced now.
So why don't you talk me through some of the reasons behind why coroutines are so important for C++?
Well, let's look how we write normal synchronous code. And in the example here, I will show how we're going to copy one stream into another with a buffer of size 512.
Got it.
So we will just copy a bunch of bytes and then we return how many bytes we copied.
All right, so in this first example, you've got the copy. This is the sort of function version of it. This is before you add any sort of coroutine.
Right. And now imagine that read and write are asynchronous functions. They do not return the result immediately. Now with coroutines, we only need to make 3 changes to this function. We'll mark up suspend points where the coroutine is suspended by placing await near stream read and stream write. And also because now function is not actually done when it returns back a future. You have to have a return type that is able to represent the idea of value is not here yet. And future is one of those types. So essentially, if you notice, we only touched 3 places. A return type went from an integer to future of int, and the points where we would like a function to suspend, awaiting for the result, are marked with await. So it looks very reasonable, not scary, very similar to a normal synchronous code. Now, for the fun part, let's see how we could have written it with futures.
All right. So let's take a look at the future version of this.
So this actually uses futures as proposed by a concurrency TS. Because futures as they exist in C++ 14 are not sufficient to do asynchronous programming. And this is more of the kind of futures proposed by concurrency TS or boost future or PPL tasks. And the code is horrible. It is inefficient, it is difficult to read, and difficult to write. There is nothing good about this code.
It does seem like a large block of text.
It is. So this is essentially a primary motivation for reintroduction of the coroutines, because we can now make asynchronous programming very similar to asynchronous one in how it looks like.
Should I think about this as this is what it's replacing, like the previous version with await in the future?
Well, I really hope that nobody would write this code. So I think people normally do not go to such trouble as to write such a complicated code. They would just hand roll a state machine by hand. So instead of using futures, you would use some kind of class which represents a state, and then you would have callbacks in that class which drive the state machine forward. So I think it will replace not that, because this is unfair. This is just horribly looking code, but it also will replace manually written state machines.
Got it. So coroutines are actually available in other languages, right?
Oh yes, they're popular. Now we're getting coroutines in Python, in Dart, in Hack, but there is something unique about coroutines in C++. The goals or objectives we set out to guide the design of the coroutine in C++.
Okay, so what does it take to make coroutines great for C++ then?
Well, let's go through all of those 5 goals. So one of them, they have to be scalable. So coroutines should be such a lightweight facility that you can have 100 million of them concurrently. So if you're doing, I don't know, a word processor, you can potentially have every character in your document to be a coroutine. I mean, not necessarily it's a good idea, but the intention is you can make as many of them as you want. They have very low overhead. Similarly, they have to be efficient so that you don't have to think twice whether to use coroutine or not. The overhead of the suspension and resumption of the coroutine is an equivalent of a function call. If you can call a function, you're okay to use a coroutine. Now, it also has to integrate seamlessly with the existing world, both C world and C++ world. So you can pass a coroutine as the callback into a C API, so that when OS is done within the sync operation, it can call you back and you can resume the coroutine. Similarly, say if your coroutine is a generator-like, which represents a lazily computed sequence of values, well, you can hook it up to the STL algorithms because that sequence can be represented as an input iterator. So you can seamlessly interact there.
So it's sort of like the yield return sort of in C#, that kind of pattern is what you mean by a generator,
Yes.
right?
Moreover, this facility is open, meaning we do not tie it to any particular asynchronous framework. It doesn't have to be just stood futures. It could be HPX futures, boost futures. It could be WinRT async operation. It could be something that you just invented. And you can go beyond just async tasks. You can try to emulate what other languages have, like language Go has goroutines. Well, go ahead. You can implement now goroutines in C++. Moreover, because in some environments you cannot use exceptions, we design coroutines in such a way that they are usable in the kernel mode, so people are free to use them in drivers.
Okay, Gor, so the scalable, efficient, and no overhead thing sounds like C++, motherhood and apple pie. Let's talk a little bit more about the open-ended coroutine mechanisms. So can you give me an example of how this would interop with other?
Oh, sure. So let's go back to the example we had in the beginning of a function that will copy asynchronously from one stream into another. That function was returning a future of int.
Right.
But coroutines are not tied to stood future of int. It could have been HPX future, boost future, PPL task, or WinRT async operation. The same with await. Like in await, we don't have to await just on stood future or HPX future or any other. We can await on pretty much anything. Moreover, you can mix and match. Your function can produce a boost future, but you can consume any other kind of future-like thing in the await.
That's really cool. Can you show me how you'd use this with more like the native operating system APIs and interop with those?
Sure. You can await on anything which satisfies awaitable requirements. Essentially, you need to explain, is the value ready already? And if it is ready, how to get it out of it? And how to subscribe for a callback to learn that the value has arrived. And the following example shows that you don't have to use any intermediaries like futures or PPL tasks. You can actually directly construct a class that will explain how to interact with raw OS APIs. And in this case, there is no heap allocations. It's completely optimizable out. So the effect would be as if you just handcrafted that in C. So now you teach await how to sleep for X number of, say, milliseconds. And we're doing that directly by going to the OS APIs, by passing any futures.
How does it know which of these functions to call for which? How do you actually wire the two together? What in this class is the wire?
I think the best analogy would be range-based for.
Okay.
C++11 got this wonderful syntactic sugar to simplify walking down the containers. And what it is doing, it is looking for begin and end.
I see.
So similarly, await is looking for three functions: await ready, await suspend, and await resume. So as long as it can find those, it will hook them in, and you're ready to go.
That helps a lot, thanks. Okay, we mentioned goroutines earlier. What's a goroutine? I'll be honest, I am not familiar with the Go language.
There is a language, Go, that was meant to solve the concurrency problems and make writing asynchronous code easier. And what they have lightweight coroutines called goroutines. And you connect them with channels, and then you represent essentially your asynchronous program as a bunch of interacting goroutines communicating to each other with channels. You know what? The facilities that we're introducing to C++ are sufficient to implement goroutine-like functionality in C++. Moreover, in the example we have here, shows that you can have 100,000 of concurrent goroutines. You hook them up together with channels, and you can just pass a value through those channels from one side to another.
That's awesome. So you can push all 100 million of these things through the channel, so that makes me wonder about perf. You mentioned earlier that this has really low overhead, and of course we have an implementation of this in Visual Studio 2015. Can you talk to me a little bit about the performance of the feature?
Sure. And I want it to be this fair comparison. So I am not going to compare that against futures. So let's see how people write efficiently asynchronous programs.
If you care about the absolute,
yes, if you care,
to the metal.
If you care about perf, they implement them as state machines, where completion of an I/O operation would drive the state machine forward. Here's an example how a state machine would look like. It's a very simple state machine. We are connected to some port. We start reading from that particular port, and eventually we will read enough, so the state machine will stop. And this is how it is usually written. It's about 3 slides worth of code. Not particularly unreadable, but it's a 3 slide worth of code. And you have to be careful to manage the lifetime correctly, because we have state machine can die because of an error during the I/O or on completion, so you have to...
Error prone in addition to being...
Yes. So now let's see how we'll write it as the coroutine. Well, we already saw the example before when we were comparing against the futures. But how much do we pay for this simplicity? Because it's a 3 slide worth of code versus 1 slide of nice looking code. Well, the interesting part that we are beating handwritten state machine on all counts.
That looks like a lot of allocations for the handcrafted state machine. Why do you have those there and not need them in the resumable functions version?
You see, a resumable function or coroutine allows your local variables to persist for the duration of the asynchronous activity. In Windows and also in AIO, Asynchronous Programming Framework, whenever you invoke an asynchronous operation, you have to have a little bit of context allocated that will persist for the duration of the operation. Now, where would you put that context? With a normal function, its lifetime is over as soon as the function completes. So you have to allocate them on the heap.
I see.
However, with coroutines, you are getting a coroutine frame that actually, with all of its local variables and temporaries, that persist for the duration of the coroutine. And because the coroutine exists until it finishes all of the asynchronous activity it needs to do, it provides a place for all temporaries required to do asynchronous I/O to stay right there.
Got it.
So it is doing much less management of temporaries for asynchronous operations.
Which is why you get to basically negative
abstractions. Not only code looks simpler, but it is also smaller code. And moreover, all of your temporaries are packed tightly on top of each other by the compiler optimizer. You don't have to manually manage your asynchronous contexts.
Great. Can we talk about any other kinds of patterns that you can implement now that you have an await?
Sure. We talked about that coroutines are functions that can be suspended and resumed. And then we looked at one particular syntactic sugar which provides meaning for suspension of a function, which is await, which says, at this point, please suspend this function until the expression we're awaiting upon is ready, so we can get the value out. There is an opposite syntactic sugar, which represents an outputting of a value from a coroutine. So when you say await, it seems like we are pulling the value from somewhere, and while the value is not ready, we're suspended. Now yield represents the opposite. At this very point, we are providing a value to somebody else, to a consumer, that will consume the value, and we're suspended while the consumer is consuming the value. At some point, consumer would want the next value. That will resume the coroutine and it'll keep going. So let's look at some non-trivial example for where would you want to use that. There is this problem called same fringe problem. It's when it is in order traversal, breadth first search traversal of two trees produces the same sequence of values. So here on the screen I have two trees which have the same fringe. Even though they're different, if you traverse them, they will produce the same sequence of characters. So we would like to write a function called flatten that, given a tree root, will give you a sequence of values representing the traversal of the tree in a particular order. And then we can trivially solve same fringe by saying, get me the first sequence, get me another sequence, and then let's call a standard algorithm equal that will compare those sequences.
Cool.
Now, imagine that your trees are really, really, really big. They have tens of millions of values. You don't want to flatten them first into some temporary structure so that you can compare. Generators allow you to produce the enumeration of the values of the nodes in the tree lazily. So essentially when you call flatten here, and flatten is a generator, it will produce values as equal algorithm.
I see.
Pulls them out to compare.
You only deal with it one by one instead of having to get the...
So at least we can see the motivation why we would want to do that. Now let's see how difficult it is to write the traversal of this tree as a coroutine. And here's the code. What I'm saying that, look, given node n, I would yield whatever I call by recursively yielding the traversal of the left, then I yield the value of the current node, and then I yield whatever is the result of traversal of the right. So it looks as if you are simply writing a recursive traversal, and in the place where you would say print out the current value, you say yield the current value. So this is another application of coroutines.
I can imagine the state machine for this thing would be a monster.
Yes, and I think in a more general fashion, when we're talking about async functions, is that with async programming, coroutines are representing a state machine, which is handcrafted, with a state machine which is expressed imperatively. And very similarly here, you have a state machine which represents the traversal of this data structure, and now you can write it imperatively, as if, hey, this is how you do it, now make me a state machine. So yes, it was a very good analogy that you said.
Right, cool. Anything else you want to cover?
If you think of what coroutines are in C++, they represent two parts. One is the low-level machinery, which allows the function to suspend and resume, and another is syntactic sugar, which hooks up this machinery to library support and allows to expand await and yield properly. Well, we actually can apply that machinery to solve other problems. For example, in some environments, you cannot use exceptions, but still you would like to get a benefit of an easy written happy control flow where your exceptional control flow is hidden. So you can use the C++ 17 coroutines to work with types like expected of t, which represents a container which stores either a value or an error.
I see.
So it looks like a future, but without the aspect of, but the value is not here yet. The value is always either here or there is an error. So you can write your code in this manner where you call synchronous APIs, but they can fail. There is a happy path where they returned you whatever they were supposed to, and there is an unhappy path where they will give you an error. So now this code is not using exceptions. Every await point has the built-in if error
I
go to
see.
end and propagate the error to the result. So this is another applications of the machinery we have.
So
for
the expected
coroutines.
int is wired up to the effectively the awaits in this thing.
Yes.
I
And
see.
this is simply an extension of what we already had for futures, because await is hooking up with future to provide the result. And now the same can be applied to types like expected, which does not have any temporal aspect to it, but it can be used with them too.
Great. So this is in Visual Studio 2015. Are we aware of other implementations?
So I know that Clang is currently actively working on it. I'm in contact with one of the major implementer. I'm not sure when it will be released.
Okay, but we are expecting to see implementations across the compilers in the industry. Ours started to be in RC or preview.
I think the first experimental version, which is roughly along the lines we talked about, was shipped in a preview, and then we have several updates to it.
Great. And so if people want to have a look at this, download the RC, or
Download
if it's out by the time
RC.
which I'm not actually sure when we're going to ship this, but if RTM's out, then go ahead and download that version instead.
Yes,
And you
yes.
should be able to get all of these headers. Is there any tricks to making sure that it's turned on in the builds?
You need to add /await to opt into this feature, because it's still experimental.
On the command line?
On the command line or in the IDE, there is the place to specify the switches. And we do have some restrictions, but we have fewer and fewer of them.
Okay, so this is our call for action for this one, is that we are hoping that folks will download Visual Studio 2015 and start coming up with your own ideas about what you can and can't do with await. And Gor is taking this through the committee and helping to champion this thing for C++ 17. If you have any feedback on the feature, Goren at Microsoft.
Yes.
Great. All right, I hope you enjoyed that episode. As we mentioned, 2015 RC has all the bits that you need, so go ahead and download them and try out await.